Hello everyone and welcome back to my channel XYZ Architect. Today we will start with a question. Have you ever had issues with colleagues that do not understand the measurement results? If the answer is yes, I hope I can help you out with this video and you can leave from here with some information on how to make colleagues understand better what we do. We will talk about graphical representations. So, let's get right to it. First of all, let's establish from the beginning what graphical representations are. So the way I see them is that they are powerful tools used by CMM programmers to show deviation directions, deformed surfaces, the limit number of characteristics, and so on. They help process engineers, tool makers, and design engineers to better understand problems from the parts and correct them even in the first correction loop. They can be used on all dimensions and characteristics, but they have the best effect when used with GD&T. So now we will go and see an example that I put together on Calypso. So I measured a part and I have a drawing, and we will talk on the graphical representations from the results from this part. This is the drawing that we are going to use for this example. The drawing is mapped with numbers near the dimensions, so it's easy for everyone to read it and correlate the results with it. So now we can generate some results on Calypso and start talking about each and every one of them. Okay, so first we have the basic report from Calypso. This is a basic report. The information here is only numerical information. We have the nominal values, we have the measured values, the tolerance, and the deviations, and a little representation here on how the deviation is on plus, on the minus, on the plus or on the minus side. Okay, so this has nothing special. Maybe some colleagues will not understand this kind of report. That's why we will need another one. We will need a plot protocol like this one, and we have here beautiful graphical representation on all of the dimensions, right? So we have the true positions, we have the roundness right here, we have the flatness, and where exactly is each and every characteristics if this is important and they want to know. We have here the profile of line. We can also change the zoom. We can make it bigger, we can make it smaller like this, or we can, I don't know, we can say, okay, I want to see it exactly like it is on the part, like this. Okay, we have also the surface deviation and so on. So now we will go through each and every one of it. Okay, so we're back on the presentation, and now we have the measurement results and the graphical representation. We have to know how to interpret them, so this is what we are going to do next. And we can start this with the true position. So we have a total deviation from the true position of 0.0055 millimeters, and we have also deviations on the axis. But on the graphical representation we can see exactly how the center point of the circle is deviated. In the left side we have the legend of the colors and what they represent. And we can see that the tolerance is represented by the black line, this one right here. The tolerance is represented by the red line, so this is the tolerance zone. It's a circular tolerance zone. If we had a warning limit activated, then we would have also a yellow line like we can see here. Let's see what else. So the measured value is represented by the green point here, and the mean value where the axes intersect is represented by the blue lines right here, right? So now it's pretty simple. Black is for nominal, blue is for mean value, the intersected axis, and green is the measured value, and the green point has to be inside the tolerance zone, inside the red circle. So if we have right-hand values like we can see here above, and a graphical representation like this, we can interpret the true position without any doubt. Of course, if we have several features to measure and we want to show which is which, then we can create a graphical representation with labels on each element, like I did here, right here. Okay, and we can see that we have a lot of information on the label as well. We have the total deviation, the nominals, and the actuals on all axes. For the flatness, we have a total deviation of 0.070 millimeters. Therefore, we have a deviation from the maximum permitted value from the flatness of 0.02 millimeters. And in the graphical representation, we have again the legend right here with the colors and what they represent. So we can see that the positive peaks are represented by the green lines. We can also see that we use two segments with scanning to make the flatness. One is represented with purple color and the other one is represented with a yellow color, and we also have the extreme points, the lowest being at 0 because flatness is always positive. In this representation we have also information on the measurement strategy. We can see what type of filter it has been used on the evaluation, and it was a low pass filter. We had an outlier of 2.5 millimeters on the wavelength. The probe radius used for scanning was 1.5 millimeters. 3 millimeters per second was the scanning speed, and the evaluation method was a minimum feature, of course. So we can see that we have a lot of information, so everyone now should understand the values. But if not, of course, we can generate another evaluation with information on maximum and minimum points from the surface and actual deviation on several points if it's necessary, like I did here. The roundness evaluation has its own legend with represented colors, as we can see here. The usual intolerance, out of warning limit, nominal value, tolerances, so we can find it right here. Intolerance we can see is right here represented. Out of warning, we do not have the out of warning limit applied. The nominal value is with black, so we have here the nominal value. The tolerances are right here, but we also have boundary of the evaluation area. The extreme circles on the outside and on the inside, so this is like and the maximum inscribed and the minimum circumscribed circle. The segment right? So the segment right here and the extreme points. Also, we have a representation of the angles from the circle from 0 to 360 degrees. This way is more easy to show the extreme points and where they are located on the circle. So like we can see here, for example, we have a point located somewhere at 290 degrees on the circle, starting from the 0 point. We also have the point number, so you can show exactly where the point is located on the CAD model if it's necessary. Some information on the measuring strategy. Notice that I didn't use any filter just for the representation to look like this, but you should always use filter and outlayer when scanning. We have the probe radius, the evaluation method, and besides the measuring strategy, we have also the measured value, the nominal, and the upper limit. Okay, now let's see how the cylindricity is evaluated. So very easy to orient on the graphical representation due to the legend where we have the axis represented by the black thick color right here. Okay, intolerance with the green color, nominal values with black thin color, and the tolerances with red color. So we see here the red color, the black color, and the green values of each measured section. We have also the heights of the sections on the cylinder, and each section is represented with its own color, so we can see its own color right here, and the extreme points as well. And on the lower side we have the usual information now on the measuring strategy, the measured value, and the upper limit as well. Of course, if it's necessary, you can generate extra evaluations like we can see here with any information that is needed. Okay, now let's move to the profile of line, where we have the legend as usual right here, with the intolerance line in green, the nominal value in black, and the tolerances right here in red. So the nominal is right here. In green it's a little deviated, so no green. Let's see if we can, yeah, we can see it a little right here, but that's it. And the tolerance is right here, so no points has to go above or beneath the red lines. The segment, this is the segment, right? So one segment, and the extreme points are here and right here. This is the minimum and this is the maximum point. Okay, also we can see in the left corner right here the information on rotations and translations if we do a best fit alignment on the section. And of course the name of the position, the measured value, the upper and the lower limit if it's the case, not the case right here, the number of points used for scanning, the filter type, the wavelength, the probe radius, the speed of millimeters per second, and the evaluation method. For the profile of surface, we have the possibility to show the sections like we did in the profile of line, and of course we can show the maximum and the minimum points like we can see here. And if it's also necessary, you can show any other information on the surface from each point from the scanned surface. And if you just use the touch trigger strategy, you can also show the touch points if you desire. The straightness plot is also interesting to show because we can see where on the surface we have deviations above the lower and the upper tolerances. This one looks like a normal plot like we use for example in SPC evaluations or in gauge R and R. So anyone who is familiar with this sort of graphics will certainly understand it. As usual, we have here also the legend in the upper left corner, intolerance with green, nominal value with black, tolerances with red, and of course we have the number of microns from the tolerance, in our case 100 in plus direction and 100 in minus directions. That does 0.2, so 200 microns. The evaluation limits, if they are activated, extreme lines. The extreme lines are right here, so it shows the extreme on the upper limit and the lower limit. The segment and the extreme points. So this is the extreme points on the upper limit and the extreme point on the lower limit. In order to orient better, we have the axis where the lines was scanned, so right here. In our case is z-axis and y-axis, so the line was scanned on the z-axis along the y-axis. Okay, and below the information from the characteristics, so the name of the characteristic, the measured value, the upper limit, the points that were used to make the characteristics, the filter type, the wavelength, undulations per revolution if it's the case, probe radius, measuring speed per second, and the evaluation method. And here we can see again some more information from the line. So it's the maximum point right here and the minimum point right here, like we saw here. It's the same points, and some other points from the line if they are interesting, and where the line was made, so we can see exactly where the line was made. Okay, so the last one is concentricity or coaxiality, because they are represented in the graphical evaluation the same. And here we have also the legend, but this time we have the connection line between the actual point and the nominal point. The tolerances, so this is the tolerance, so this point does not have to go through this tolerance, like we can see here, the round tolerance. The actual point that says that intolerance, the extreme points, that it's the same as the actual point and the nominal point right here. So we can see that the segment one has a deviation of 0.0183 millimeters. Okay, so below we have the name of the characteristic, the measured value, the tolerance, number of points used, the filter type, the wavelength, undulations per revolution, the probe radius, measuring speed per second, and the evaluation method. Of course, you can show more information from the feature if you like I did here. Okay, so this is it, guys. I hope now you understand how to look on the graphical representation. If you like, you can show this video to your colleagues from the other departments if they have problems interpreting the graphical representations. I'm sure if they will watch this, they will understand better. So leave a like if you like what I did, subscribe if you are not a subscriber yet, and until next time, have a nice one.